This is a video on Le Chatelier's principle. Le Chatelier's principle states, if an external stress is applied to a system in equilibrium, the system adjusts in such a way that the stress is partially offset as the system reaches a new equilibrium position. What does that mean? Well, we've got our system in equilibrium, and there's different ways of stressing it out, causing our equilibrium to undergo a stress. Remember, an equilibrium is a situation in which the two opposing processes are happening at the same time and at the same rate. And of course, during the process of change that occurs in the forward and reverse reactions, we know that the concentrations of each of the substances stays constant. So we have this constancy and we have change taking place at the same time. If you do something to the system, it offsets that constancy and it places a stress on the system. And the system will always react in such a way to partially offset that stress and reestablish equilibrium. We're talking about some type of stress that affects the equilibrium. Remember, if we go back to, let's say, I went a little too far back. This slide here. Remember this this equation that we gave you previously, that the hydrogen and the iodine are reacting to form 2HI, and of course there is the equilibrium process that's taking place, and we're going a little too far. What I really wanted to show you was the equilibrium expression here. Okay, remember the equilibrium equation is based upon the law of mass action and based upon hydrogen iodide being the product and hydrogen and iodine being the reactants. We see that the K sub C is equal to the HI concentration squared divided by the H2 concentration times the I2 concentration. It's just the law of mass action. So remember that if we add reactants and products to the vessel, these concentrations will work their way and change, and we will, until this is true, that the concentration of the HI2 at equilibrium divided squared, of course the HI squared, divided by the concentration of the H2 times the concentration of I2 is equal to the K sub C, a constant. So whatever these concentrations start out as, right, whatever we add these two, to the container, whether it's all H2 and I2 or whether it's all HI, we will establish an equilibrium between the three. And of course, those concentrations have to, when placed into this equation, come out to be equal to the K sub C. So that means when we place a stress on the system, we want to reestablish that equilibrium because of the fact that the law of mass action says that the concentrations of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients must always, no matter what, come out to be equal to the K sub C. So if we place a stress on that system, it's going to try to offset that stress in order for us to get back to equilibrium and back to the fact that the concentrations follow the law of mass action, that the concentrations of the products over the concentrations of the reactants end up being equal to the K sub C. And so one of the stresses is change in concentration. So going back, let's take a look at this reaction here. Nitrogen gas reacts with hydrogen gas in a 1-to-3 relationship. It'll form NH3 gas. And of course, the reaction could be in equilibrium. So we establish an equilibrium. The reaction is taking place in the forward reaction, and the reverse reaction is taking place. Those are both happening at the same time and at the same rate. The concentrations of each of these species remains constant. And of course, the concentration of the NH3 squared divided by the concentration of the H2 cubed times the concentration of the N2 follows the law of mass action, and they're equal to, that ratio is equal to the K sub C. So let's purposely put a stress on this reaction by adding NH3 to the system. So by adding NH3 to the system, remember, we have placed a stress on the equilibrium. We now have more NH3 than we would normally have under those conditions at equilibrium. Because remember we said that at equilibrium, the concentration of the NH3 squared divided by the concentration of the H2 cubed times the concentration of the N2 has to be equal to the K sub C. It follows the law of mass action. We disturbed it by adding more NH3. Now it has more NH3 than it should at equilibrium. We've disturbed that equilibrium. We place a stress on it. So how is the equilibrium going to behave? What's it going to do? Well, it's going to try to partially offset that stress and reach a new equilibrium position. So in order to do that, in order to add, when we add NH3 as the stress, the equilibrium is going to shift to the left in order to offset that stress. In other words, if there's too much NH3, that means it's not following the law of mass action, and so we've got to have this equilibrium shift to the left-hand side. So the rate, or not the rate, but the NH3 is going to move to the left. It's going to shift to the left, and more N2 and H2 will be produced, and less NH3 will be produced from the forward reaction. And it's trying to reestablish that equilibrium. And we see here that if this was the initial concentration of H2 at equilibrium, and this is the initial concentration of NH3 at equilibrium, and this was the initial concentration of N2 at equilibrium, we see that there's a spike in the concentration, so we changed it really quickly because we added it, and we see that the NH3 concentration is going to drop, the H2 concentration is going to increase, the N2 concentration is going to increase, and of course, since this is a 3-to-2 relationship, as we see here, it's a 3-to-2 relationship, this concentration is going to jump up 3 times the N2 concentration. Excuse me. And therefore, we're going to reestablish equilibrium, and we notice that the concentrations were not the same as they were initially. The NH3 concentration is still greater than it was to start with, but it has lowered, excuse me, because as we showed you, the reaction has to shift to the left. It's going to make more H2 and more N2 while reducing the amount of NH3 that it makes, shifting to the left, so it's reducing the NH3 and making more H2 and N2 in order to remove some of that NH3. Can't remove all of it. Can't remove all of the added NH3. We're going to remove some of the added NH3. And again, we see that the equilibrium concentrations, the new equilibrium concentrations for each of the species is going to be higher than it was to begin with. Changes in concentration outlined. Well, for a reaction which A with a coefficient of A reacts with B with a coefficient of B, to form C with a coefficient of C and D with a coefficient of D, if we add any one of the products, either one, it's going to shift to the left to try to reduce the amount of products and increase the amount of reactants to re-establish equilibrium. So an increase in the concentration of the products causes a shift to the left. If we take away some of the products, remember now we don't have enough product and it's not following the law of mass action. So these concentrations on top of the equation are now smaller than they were, and now what has to happen is it has to shift to the right in order to try to make more of the concentrations of the C and the D, the products, in order to get back to equilibrium. And so if we decrease the concentration of the product, it's going to shift to the right to try to make more of the products. So we reestablish equilibrium, get back to a situation in which the concentrations, when plugged into the law of mass action, still give us the value of the K sub C. If we add reactants, again, now we have too much reactants, and the value that we are going to establish is going to be now smaller than the K sub C, so it's going to shift to the right in order to try to make more products and reduce the amount of reactants, of course. And in that process, we increase the concentrations, it's going to shift to the right. Let's remove some of the reactants, therefore lowering their concentrations. And of course now we've reduced the amount of the two reactants, and so now we're going to have to shift to the left in order to try to make more reactant, which will reduce the amount of product. And so decreasing the concentration of the reactants causes it to shift to the left. So in summation, If we increase the concentration increase the concentration of the product, it's going to shift to the left to try to make more reactants to reestablish equilibrium. And if we decrease the concentration of the product, it's going to shift to right, making more product to reestablish equilibrium. If we increase the concentration of the reactants, it's going to shift to the right, making more product and reducing the amount of reactants in order to, again, reestablish equilibrium. And if we decrease the concentration of the reactants, it's going to shift to the left, again, to also try to make more reactant, because if we took some out, it's going to try to put some back, reestablish the equilibrium, get those concentrations back to where they should be so that the law of mass action is followed. But remember that the concentrations that are reestablished are not going to be equal to the initial concentrations at equilibrium that were established to begin with. Changes in volume and pressure. Changes in volume and pressure, my friends, affect the equilibrium. Okay? Think about Boyle's law. Boyle's law says that if we increase the pressure on the gas, the volume of the gas is going to decrease. And if we decrease the pressure, the volume is going to increase. So, based upon Boyle's law, pressure and volume are inversely related. As you know, molarity is the number of moles of substance, solute, divided by the volume of the entire solution. So in a sense, my friends, you can almost think of this as kind of a mixture. It is a mixture. I mean, we have reactants, we have products, we have them all mixed together in the container, even though there's a chemical reaction taking place between A and B to form C, and they're all gases, as you can see. You can kind of think of it as a mixture too. Now remember, pressure affects volume, and volume is part of the molarity equation, number of moles divided by volume. So if the pressure changes the volume in turn therefore changes the molar concentration. So by changing pressure, we change volume, and by changing volume, we actually end up changing the concentration. And that's how this becomes a stress in terms of this equilibrium. Of course, one can change the volume on purpose, and then that would cause the pressure to change. But changing the volume itself, since it will affect the concentration, is really the factor that affects the equilibrium. So changing pressure causes a change in volume, and it's the change in the volume which causes a change in the concentration, and therefore a change in the equilibrium. And of course, this really only applies to situations in which at least one of the species in the equilibrium is a gas. If none of them are gases, then this slide is not even worth talking about. But since we are talking about there are many reactions in which at least one thing is a gas, this becomes an important slide. So if we increase the pressure, that obviously decreases the volume. If we decrease the volume, that changes the concentration. It makes the concentration actually go up. What's going to happen is it's going to shift to the side with the fewest number of moles of gas, because increasing the pressure decreases the volume, which makes the concentration of each of the gases go up. And what's going to happen is, since the concentration of each goes up, it's going to try to shift to the side with the fewest number of moles of gas in order to reduce those concentrations. So it's going to reduce the concentration. So if we increase the pressure in this case, it's going to shift to the side with the fewest number of moles of gas. On this side there are 2 moles of gas. In this side there's only 1 mole of gas. So it's going to try to shift to the right, because this is the side with the fewest number of moles of gas. Decreasing the pressure obviously is going to increase the volume. Increasing the volume is going to cause the concentration of these to actually decrease. And so what's going to happen is it's going to try to shift to the side with the greatest number of moles of gas and try to increase the concentrations on this side. And so it's going to shift to the left, making more of A and B and less of C. Let's increase the volume. Increasing the volume is the same as decreasing the pressure. Because remember, decreasing pressure will increase the volume, and therefore increasing the volume gives you the same result. And therefore it's going to shift to the side with the most moles of gas again. So increasing the volume is the same thing as decreasing the pressure, and it's going to shift to the left in this case because there are the greatest number of moles of gas. Decreasing the volume is the same thing as increasing the pressure, and it's going to shift to the side with the fewest number of moles of gas. So in this case it's going to shift to the right in order to go to the side with the fewest number of moles of gas, and we can see that in terms of the arrow. Temperature. Changing the temperature, as you remember from the Arrhenius equation, changes the value of little k. And of course, changing the value of little k, which was not discussed in a previous video, which really isn't necessary in terms of the AP test, but I will give you a little bit of information. It turns out that the k sub c is equal to k forward, little k, that is the rate constant. K sub c is equal to little k forward divided by little k reverse. So since big K, the equilibrium constant, is dependent upon the rate constants in the rate law, changing the temperature, as we saw in the Arrhenius equation, affects little k, and then of course since big K is equal to little k over little k for the forward over the reverse, changing little k affects big K. So increasing the temperature is going to disfavor the exothermic reaction. It's going to cause K to decrease. Increasing the temperature will favor the endothermic reaction and cause K to increase. Decreasing the temperature favors the exothermic reaction, causing K to increase. And decreasing the temperature does not favor the endothermic reaction, causing K to decrease. Remember, increasing our temperature, right, for an exothermic reaction doesn't really make sense in terms of helping it, okay? Because the exothermic process is giving off heat. And if you raise the temperature, you're not absorbing the heat. The endothermic process absorbs heat. And so if we raise the temperature, we're increasing the amount of heat. That's going to cause the endothermic reaction to shift to the side where we have the products, and K will decrease for the exothermic reaction and increase for the endothermic reaction. Decreasing temperature, K increases and K decreases, because again, decreasing the temperature removes heat, and exothermic reactions, that's good. You're taking heat away from it. It's removing heat from a situation in which it's producing heat, and so it's going to cause it to increase the value of K, therefore making more product, and decreasing K, making less product, more reactant. Le Chatelier's principle. Continue. What we have here, my friends, is an uncatalyzed reaction and a catalyzed reaction. This is going to be your favorite part of Le Chatelier's principle because adding a catalyst doesn't change the value of K, and therefore it doesn't change the equilibrium position of the system, and therefore basically the only thing that's going to happen is adding a catalyst will make the reaction reach equilibrium sooner. It doesn't change the position of the equilibrium. It doesn't affect the equilibrium whatsoever. We just end up at equilibrium quicker. And so that's why you're going to like this, because if I ask you a question, how does a catalyst affect the equilibrium of a reaction, you just say, well, it doesn't. It just makes it reach equilibrium more quickly. A catalyst lowers the activation energy for both the forward and the reverse reactions, and therefore that is why it has no effect on the equilibrium. The only thing that it does is make the equilibrium be established more quickly. Okay. So that's pretty much it. A couple of slides, chemistry in action. This is a chart of it gives us a whatchamacallit, a chance to kind of take all that information that we've just talked about in this video and review it. So take a look at this slide, and when you're ready, that will be the end of this video and pretty much the end of the chapter. And I apologize if this is not the greatest video in the world. I'm a little off this week. Unfortunately, I picked our break to get sick. So don't be afraid to ask lots of questions in class. And I think we're probably going to have to go over that temperature information a little bit more, because although this slide tells us some good information about K and how it affects K, it doesn't really address some things that we're going to need to talk about. So this will be something that we can talk about on Monday. So enjoy the rest of your vacation, and we'll see you on Monday.